So in the lecture on sampling theory, we discussed what are the conditions that you need if you are sampling a band limited signal. Let's say your voice, you're recording it. What is the frequency that you need to use to sample that signal? How often you need to sample that signal? And we understand that aspect that if G of t is band limited to omega m radians per second, then we better sample it using frequency at least 2 omega m. So let's say we do that, we get Ga of t, and we pass it through an ideal continuous to discrete converter with sampling period time t, and we get G of n, which is simply samples of your signal every t seconds. The question is, how do we then, once we have those samples available to us, how do we reconstruct the original signal from those samples? And that is something that arises, for example, in any recording that you do with respect to voice, speech, songs. You record these signals, and then at the end of the day, you are interested in playing them back. You are interested in reconstructing them in the continuous time. So how do we do that? That's the focus of this lecture. And again, we'll look at formally what is the hardware operation that you need to do, but we'll first break that operation of reconstruction down into two pieces, just like we broke it down into two pieces for the sampling procedure to understand what we need to do. So let's say you are given the samples Gn. The first thing we do is convert from sequence to an impulse train. So in the sampling lecture, we had talked about that the conversion from the impulse sample signal to the sequence, or the sequence to the impulse sample signal, that's mathematically an operation that doesn't lose any information. So let's say you are given time period t, you use Gn to construct this Gp of t, which is given by G of n delta of t minus nt. So you just take your samples and you put down impulses every t seconds, and the area of those impulses, if this is t equal to 0, the area of this impulse will be G0. If this is t equal to capital T, the area of this will be G1. Let's say this is G2 at t equal to 2t, and so forth. We can go back and forth in these two things without any loss of information. Now, in our original formulation, when we were doing the sampling theory, we understand that if this Gn came from a continuous time signal, then this Gp of t, the Fourier transform of this signal, is related to the Fourier transform of the original signal through a summation formula. We studied that the Fourier transform of the impulse sample signal, that is given by, we talked about three main properties of sampling, that the transformation of a continuous time signal to its impulse sample signal. So mathematically, we can write that Gp of j omega, here is the scaling, here is the periodic repetition of Ga of j omega minus k omega t. Okay. Each copy is separated by 2 pi over t in the frequency domain. So in reconstruction, our goal is, we already know when GP of j omega contains all the information about the original signal. There is no loss of information in GP of j omega about the original signal GA of j omega, as long as different copies of GA of j omega don't overlap with each other. Which is precisely the Nyquist sampling criterion that we had derived, that your sampling frequency must be greater than twice the bandwidth. If you do that, then there will be no overlap of multiple copies. So let's assume that there is no overlap. How do we recover the signal from this impulse sample signal? Now we can address that question mathematically, but let's look at it first graphically. This is the Fourier transform of your original signal. From the samples of the signal, you construct the impulse sample signal, the periodic impulse train signal, GP of t. So this is the Fourier transform of that. Here is the situation where you know that the Nyquist criterion is satisfied, your sampling frequency is twice the bandwidth, so there is no overlap, there is separation between different copies. Right? Now the question is, how do you recover GA of j omega from this? We are looking at in the frequency domain. If we understand the frequency domain operation, we know what the time domain operation will look like anyways. So this is what we want, and this is what we have, these periodic copies. The question is, how do we recover it? So if we low pass filter anywhere between these points, we'll get rid of all these copies and additional copies. And if the height of this low pass filter, we make the height of the low pass filter t, then it will get multiplied with 1 over t and we'll get 1. So this is what we get once we low pass filter with height capital T. Okay. Now, this is the low pass filter. It is usually used with a subscript R to say that this is a reconstruction low pass filter. Why we call it reconstruction low pass filter? Because unlike most low pass filters, this low pass filter has a scaling factor of capital T, which is a function of your sampling time. And also, the cutoff frequency of the low pass filter is taken to be 1/2 your sampling frequency. So the cutoff frequency is taken to be omega t over 2, or which is equal to pi by t. Because you know that if you sample the signal, once you sample a continuous time signal, you cannot preserve any frequency that is above the sampling frequency divided by 2. Last lecture we talked about 2 ways of looking at the sampling theorem. One is, you are given a bandwidth, then you need twice the sampling, your sampling frequency should be twice that bandwidth. Or if you are given a sampling frequency, then there should be no frequency in the signal that is more than 1/2 that sampling frequency. So the low pass filter is constructed with a cutoff of pi by t, or the sampling frequency divided by 2. So if we are doing a block diagram, what it says is we take our impulse sample signal we pass it through a low pass filter HR of j omega, and we'll get back g hat A of t, and this g hat A of t will be equal to g A of t, the original signal that you started with, if the Nyquist criterion was satisfied and if your low pass filter was an ideal low pass filter. So the reconstruction low pass filter, we typically assume that it's ideal. Its height is t for all frequencies less than or equal to sampling frequency divided by 2, which is pi by t, and it's 0 otherwise. So this is what it looks like in the frequency domain. The height is t. Whenever we say reconstruction low pass filter, just keep that in mind. The height is t instead of the typical thing of 1. Okay. Now we can verify that mathematically also, that if you multiply multiply the frequencies of your signal GP of t with this low pass filter's frequencies, then you get back the original signal. So let's write, so the Fourier transform of this, we'll write it as g hat A j omega. What's the relationship between the frequencies of the output with the frequencies of the input and the filter? So g hat A of j omega is simply gp of j omega times hr of j omega. And now we just plug in the values. So we know gp of j omega is 1 over t, summation k from minus infinity to infinity, ga of j omega minus k omega t. This is gp, and hr of j omega is, I'll use this notation, t times the indicator function, which means that this whole thing is 0 outside the range minus omega t by 2 to t omega t by 2. Okay. So now I multiply. Of course, the t's cancel. J omega minus k omega t, and I get this indicator function of minus omega t by 2 to omega t by 2. Now, to analyze this term in each summation, we have to focus on different cases of k. So if k is not equal to 0, then GA of j omega minus k omega t, right? Any copy that is not around 0 is outside the omega t by 2 to omega t by 2 minus omega t by 2 range. It lies outside that range of minus pi by t to pi by t, just like we saw in the previous picture. So if k is not equal to 0, this product is simply equal to 0, because this whole thing is lying outside the minus pi by t to pi by t range. And if k equal to 0, then GA of j omega times 1 omega will be simply equal to, you're multiplying it with 1. So that will be equal to GA of j omega. So you collect all of these facts together and you get G hat A of j omega equal to GA of j omega. Now the assumption here, of course, is that you started with satisfying the Nyquist criterion. There were no overlaps of different copies. Otherwise, you cannot do what we just derived, right? So while this expression will still be true, the end result won't be true. Now in time domain, of course, that means that g hat a of t equals g a of t. So that is just mathematically confirming what we saw earlier, that if you take your impulse sample signal and you low pass filter it, you get back your original signal that you started with, that you sampled. So in block diagrams, you are often shown this figure that Gn goes in, and people say D discrete to continuous with capital T, and you get back some G hat A of T. What this operation means is that you are using an ideal low pass filter, and this operation mathematically is divided into these two blocks: sequence to impulse train. You first construct GP of T, and then you have an ideal low pass filter HR of J omega. And of course, in both these blocks, you need the timing duration, and you get back G hat A of T. Now also keep in mind that if you want to go from signals to samples and then samples to signals back, the time period should be the same in all the blocks. So if you have a recording of someone that you recorded at 44.1 kilohertz, but when you are reconstructing that, you input, let's say, 60 kilohertz as the sampling frequency, then all of these things will be messed up. We'll look later what could be the effect of that operation. But for the time being, we are assuming that the sampling frequency that is input to all blocks remain the same. If you record something at 44.1 kilohertz or 20 kilohertz, you have to play it back at the same sampling frequency. Now, as we talked about earlier, this operation of first convert to impulses and then low pass filter, is this really necessary? How do you do it in hardware? It turns out that actually we don't really need to do this operation, and we can instead do something very simple, which is called sinc interpolation. So which is just an equivalent version of explaining this reconstruction. So remember what GP of T is. GP of T is written as n from minus infinity to infinity, G of n, delta of T minus NT. And then we are low pass filtering it HR of J omega to get back G hat A of T. Now, HR of J omega. So previously we looked at this operation in frequency domain. Let's now look at this operation in time domain. So HR of J omega, which we said is this ideal box filter for omega less than or equal to omega c. The cutoff frequency is pi by t and 0 otherwise. This filter has an impulse response Hn, Hrn. I'll write it to specify the reconstruction filter. So the impulse response of this low pass filter is sine of omega ct, where omega c is pi by t, over omega ct, the sinc function. So let's now look at this operation of low-pass filtering in time domain. We have g hat of t that is equal to, so it's convolution of the input signal with the impulse response of the filter. So let's plug in the input signals form, that is n from minus infinity to infinity, g of n delta of t minus nt, convolution with hr of t. We are in continuous time, hr of t, hr of t. Okay, now I'll just use the linearity property of convolution. I'll write n from minus infinity to infinity, g of n delta of t minus nt, convolution with hr of t. So the output of this convolution is simply going to be the impulse response back shifted at the location of the impulse, which is nt. So I get that form. I get that n equal to minus infinity to infinity g of n hr of t minus nt. So that is what my g hat a of t looks like. This expression is true regardless of what my reconstruction filter is. True regardless of the choice of hr of t. But for the special case where the reconstruction filter is the ideal low-pass filter, the special case where hr of t is sine of omega ct over omega ctt, this sinc, in that case we know that g hat of t equals to ga of t. We proved it earlier using the frequency domain formulation. So if we now look at this reconstruction, we see that we don't really have to form any impulses. Our output could simply be, our output is a function of g hat a of t in this case is simply a function of my sequence g of n times sine of omega c t minus nt over omega c t minus nt. This formula is called the sinc interpolation formula, which simply means that what you're trying to do is you're given some samples and you are trying to fill in the values in between those two between different samples using the sinc function, using the sinc kernel. Okay. And if all the conditions were satisfied, like you satisfied the Nyquist criterion and there was no aliasing, then you are guaranteed that that sinc interpolation will give you back the original signal. This is what sinc interpolation looks like. You start with these samples. You are only given these samples. In your hardware, you have access to a few samples. And what you do is, with each sample, you put a sinc at the location of the sample. So and the height of that sinc is proportional to the sample value. So at this location, you put a sinc, and this sinc keeps on going. At this location, you put a sinc whose height is proportional to this sample value. Then you put a sinc at the next location whose height is proportional to that sample value. Then you put a sinc at the location of the next sample value, and you keep on doing that. I'm only drawing parts of the sinc. Of course, the sinc keeps on going forward and forward. And you only had these small number of samples, but if the samples really came from a band limited signal, and if you add up these infinite sincs that go on to infinity, if you add up these sincs, then as if by magic, if you add them all up, you will get back all the values of the signal in between the samples. Where if you add all these sincs up, you get back all these values, and this is what your signal in this case looks like. And you can really experiment with that yourself too. Just, for example, take samples in MATLAB of maybe a cosine, and then just use MATLAB to add those samples using this sinc interpolation formula. And the more sincs you keep on adding, our original sinc interpolation formula involves an infinite number of sincs. But as you keep on adding more and more sincs, you will start to approach the original signal closer and closer. Okay? So if you look at the sinc interpolation formula, you see that there is no real point of going to the impulse train that we talked about. That is more for our convenience when we are doing the mathematical analysis. So the two basic lessons of this discussion are that, number one, if you sampled a continuous time signal by satisfying the Nyquist criterion, then you can reconstruct the original signal without any distortion, as long as you use a perfect reconstruction filter, which is a low pass filter with a cutoff of pi by t and a height of capital T. And second, that you can also do that same operation in time domain using the sinc interpolation formula, which is simply a summation, and you simply add an infinite number of sincs where the height of each sinc is proportional to your sample value, and the location is at the location of where you originally took the sample.